Welcome to the mini lecture on Chapter 8, Economic Growth. First, why should we study economic growth? Why some countries are prosperous, become prosperous, and others do not, really is the core question of all macroeconomics. In some ways, it's the core question of economics, going back to Adam Smith in his book, The Wealth of Nations. We call it The Wealth of Nations. It was actually, I think I have this right, an inquiry into the causes and consequences of the wealth of nations. In the title, he's saying this book is about why some nations are wealthy and some are not. Let's see. We have here, if you download the PDF of these lecture slides, there are links here to some data. In some countries, like the United States, you're almost guaranteed that your baby will live. In other countries, that's not true. Economic growth has a very real effect on people's lives. So I'm not going to go into that further right now. We're going to start with the Solow growth model. Robert Solow won the '87 Nobel. He won the Clark Medal, which it's for the best economist under age 40. It's considered a precursor to the Nobel. He won that in '61. He is currently, I think, 96, 95, 96, 97, in that range. I love this quote of his. If God had meant there to be more than two factors of production, he would have made it easier for us to draw three-dimensional diagrams. You know, in the principles class, having to express multivariable concepts on a two-dimensional whiteboard, it's a challenge. Every teacher faces the same challenge, and that's true. Anyway, that just amuses me. Okay. The Solow growth model. Capital in this model is not fixed. It can accumulate over time or degrade over time. It's not exogenous. Also, in the Solow growth model, everything is on a per worker basis. Capital per worker, we call that effective capital. Output per worker, well, that's your standard of living. Okay, there's no government, no taxes in this model. Keeps it nice and simple. Output. We know that's a function of, whoops, that's not what I wanted. There we go. It's a function of capital and labor in the previous model. But here, we're dividing through everything by the units of labor. So lowercase y is output per worker. Lowercase k is capital per worker, which means that now output per worker, the production function, is only a function of one variable, capital per worker. Simplifies things. Now, this is the production function, capital per worker output per worker. Output per worker is just a function of capital per worker. Notice, diminishing marginal product. If you add a unit of capital, and you currently have very little capital, let's say that much, so you have this level of output per worker, and you add a unit of capital per worker. It has a big increase, relatively, in output. That kind of should make sense. If you have very little capital, getting some will allow you to increase production a lot. But if you already have a lot of capital and you add another unit, output does go up, but by very little. If you're already swimming in capital, one more unit's not going to help much. Declining marginal product. That's why the production function is shaped like that. Okay. Now, in this model, the one exogenous parameter is the savings rate. S. Consumption for each worker on a per worker basis. It's equal to output times the amount not saved. If you're saving 20%, 1 minus 0.2 would be 0.8. You're consuming 80%. All right, that's not complicated. Okay, we start with this. Output per worker as a function of capital per worker. For a particular level of capital per worker, this will be the output per worker, Y1. That output will be divided into two parts. Part will be consumed, part will be invested. That's the amount consumed, and that's the amount invested. Well, investment equals savings. We're not dealing with exports. So, if this is production per worker as a function of capital per worker, this is consumption per worker as a function of capital per worker. So, the savings rate times output is the amount of new capital that's being created per worker. So keep an eye on these variables. Remember that f of k, that's all on a per worker basis, is output. This s f of k is investment. The key is that this is the rate, this is the amount of new capital being added to the economy. Now here's a separate curve. You already have some capital. In this model, capital does not last forever. It wears out. Depreciation. And it wears out in this model at some exogenously fixed rate, which is lowercase delta. If the depreciation rate was 0.2 and you have 100 units of capital and nothing else changes, next time period you'll only have 80 units of capital because 20% was used up, worn out. So this curve is how much capital is going away as a function of capital per worker. If you have this much capital per worker, you're going to lose that much per time period. If you have a lot of capital per worker, you're going to lose more per time period. So if you're out of your production, you're saving some and creating new capital, adding capital to the economy, and at the same time, some of the existing capital is wearing out and exiting the economy, then in steady state, the rate at which capital is being accumulated has to equal the rate at which capital is depreciating. So, and if they're not equal, if you're not in a steady state, if you're accumulating capital faster than it's wearing out, then capital will build up. Delta K will be a positive. Okay. There's your steady state when that is true. You put both graphs, you plot them both at the same time. This is the rate at which capital is accumulating. I'm sorry, this is the amount of capital that you are adding in each time period. This is the amount of capital you're losing. So, if you are here with this amount of capital per worker, then the amount you're gaining and the amount you're losing are the same, this much. So the total stock of capital is not going up, not going down. This is a steady state. What happens if you're not at the steady state level of capital per worker? Let's assume you have less capital per worker than the steady state of K star. Okay, let's look at the two parts separately. Just looking at accumulation of capital. How much capital in each time period are you adding to the economy? Well, if this is the amount you're saving, and this is the amount you're losing, then here, delta K is a positive number. You're adding more than you're losing. If in every time period you add 100 units of capital, but you lose 80 to depreciation, that means each time period you're gaining 20 units of capital. So here, in the next time period, you're not going to be at K1. You're going to have a little more capital than that. And you're going to add some more the next period and the next period. You're going to end up adding capital every time period until you reach this level of capital per worker. And there's what I just drew. And the process repeats in the next time period. You still have less than the steady state level, so you're going to gain more again, that much. Now, what happens if you have more capital than the steady state level? Let's say you have K2 capital per worker. Well, that means that you're going to add the savings rate times output per worker. You're going to add that much capital in the next time period. But because you already have so much capital, you're losing a lot to depreciation. How much? Well, that much. You're losing more than you're gaining. which means that this term, the difference between the two, delta K, is a negative number. Capital's wearing out faster than you're replacing it, which means over time, your capital per worker will go down. And the same thing will keep happening. You'll end up, if you, actually go back, there. If you have less than the steady state level of capital, you'll gain. If you have more than the steady state level of capital, you'll lose capital. Either way, over time, you're going to end up at the steady state level of capital, because this is the only point where the total amount of capital you have is neither going up or down. Let's see. Solow model makes some predictions that countries with higher savings rates will have higher levels of capital and therefore income per worker. Well, you can see that there is a positive relationship. Not terribly tight, but it's certainly consistent with the model. Now remember, the savings rate is exogenous. We're just saying people save blank amount. But since it's exogenous, we can choose to use a different number. What happens if the savings rate changes? The two exogenous variables here are the savings rate and the depreciation rate. Let's say the savings rate goes up. If you're in the steady state level of capital per worker at savings rate 1, you're going to have that much investment and savings and depreciation. The amount of capital you're losing and gaining is the same, and you'll be at this steady state. If the savings rate goes up, well, think of that as a momentary shock. All of a sudden, the savings rate goes up. Savings is used to produce capital. So all of a sudden, you're going to be accumulating more capital. But for that brief moment, you still have the existing stock of capital that's the same size. So your depreciation, your loss of capital to depreciation, hasn't gone up yet. So momentarily, you'll be adding more than you're losing. You're just moving to a new steady state, which is where the two curves cross. You'll end up with more capital per worker, gaining more and losing more each time period in the new steady state. This link will take you to, actually I think it takes you directly to the Solow model, but you can just, back up one in the, well, I'll show you. Up here in the address bar, oh wait, you can't see that, sorry. Let me get that where you can see it. Oof, and it's not cooperating. Give me just a moment. Okay. Nope. Sorry, having a little... There we go. And there we go. Takes you to this simulation. You can click here and it will show you all the different simulations it has. And we'll be getting to these other models later. But for now, Solow growth model. This is nice because it lets you play around with it. You can change the depreciation rate and the savings rate. Now, notice here, this adds an extra curve. F of K, this is total output per worker here. savings rate is S, so this red line is capital accumulation per worker per time period. And this is the amount of capital times the depreciation rate. So red is what you're gaining, blue is what you're losing. Let's say you find a way to make capital last longer so that the depreciation rate goes down. Well, your steady state of capital is going to go up, and your output per worker, the standard of living, is going to go up. It'll go up to a new steady state and stop there. Let's put it back where it was. Now, let's say your savings rate drops. Well, that's taking the red line down, so you're going to move left to the new steady state level of capital, which will be lower. And instead of having this level of output per worker, you'll only have this much. Standard of living will go down. A key insight of this version of the solo growth model is if your savings rate goes up, now look here, at these initial values, at the first steady state level of capital per worker, here, it's right above like the A in Keynesian, so you can visually follow it. It gives you this level of output per worker. This is your standard of living. What happens if the society starts saving a larger fraction of income? Well, instead of having this level, this living standard, you have a higher living standard. If the savings rate goes up, the standard of living will rise. But the savings rate has to stay at that higher level forever to maintain this new steady state level of output per worker. What it means is if you increase the savings rate, the standard of living will go up, but it'll only go up to a certain point, the new steady state. Your economy will grow and then stop growing when it reaches the steady state. You will not have any further increases in the standard of living, but you'll have to keep saving at the higher rate forever. So increasing the savings rate bumps you up to a higher standard of living, but it's a one-time deal. It doesn't increase the rate of growth permanently. Okay, let's see what else I want to show you here. All right, the golden rule. There are two equilibria here. One is the steady state. The steady state is where the amount of capital you're accumulating and losing is the same. Given savings rate S1 in this economy, it's K1. This is the amount of capital that you'll end up at. This is the amount of savings and investment each time period you'll end up at, and it'll stay there forever. But remember, this is not f of k. This is s times f of k. F of k is output. S times f of k is a fraction of that output that's being saved to produce new capital. So we're going to add a new, if I can find it, well, they show it here, a new curve. What we were looking at was these two, the red and blue. But you have to keep in mind that this is just savings. This is total output. This is the one you really care about because this determines your standard of living. So always in the background, remember there's this other curve above this one. That is relevant in the golden rule steady state. In this graph, before we get to golden rule equilibrium, there really isn't one steady state. There isn't one equilibrium. There are an infinite number of equilibria, depending on your savings rate. If you have a low savings rate, let's see, then this curve would be there. And this would be your steady state level of capital. And so just as this can be an equilibrium with the right savings rate, well, a different savings rate gives you that equilibrium, and a different savings rate gives you that equilibrium level of capital. And because the levels of capital for all these different equilibria correspond to different standards of living. Which means if you have all these different possible steady states, depending on the savings rate, well, let's assume the depreciation rate is just fixed. You can't do anything about it. But the savings rate, that's a human action. The society could choose to change the savings rate. Hey, everybody, let's all start saving 12% more or 20% less. So you actually can choose which of these steady states you want to be in by adjusting your savings rate. Now, if you can choose multiple different steady states, which one should you choose? Which one do you want? You want the one that maximizes consumption. Okay. Here, note, this is total output, not S times F of K, not new capital. The new capital curve would be some fraction of that. Whatever your savings rate is times F of K, and that would be, you know, something somewhere below that curve. Okay. If this is total output, and this is how much capital you're losing every time period, in a steady state, just, I'm not saying which one, but just a steady state, the amount of capital you're losing is equal to the amount of capital you're creating, because its total's not going up or down. Well, that means that this delta K is how much you're losing, but it's also how much you're replacing. This is how much new capital you're creating every time period to stay in a steady state. New capital is created from savings. So if you are in a steady state, this is also your savings rate, because savings becomes investment, becomes new capital. So this curve, this line, shows you, if you're in a steady state, how much you have to save every time period. Well, if this is how much you're saving, and this is total output, then what is that? You are saving that much, you're producing that much. The difference between the two is consumption. So the area between this curve and this curve is consumption. If the amount you're producing is greater than the amount you're saving, then you have some positive level of consumption. If you were out here, well, you'd be trying to save more than the total. You'd have negative consumption, which you can't have. So this right there, that distance is how much you're consuming. If you were in a steady state down here, notice that these are all in this graph steady states. Before, they weren't all steady states. Only one of them was, because you're showing a particular savings rate. Here, we're assuming any possible savings rate. And for each savings rate, what is the steady state level of capital? Well, that's all of these. So you can pick any steady state level of capital you want by adjusting your savings rate. The one you want, the one that you would choose, is this one right here, because this is the one where the distance between these two is greatest. Consumption per worker is maximized. You have the highest possible standard of living. Now, how can you find this is called the golden rule steady state, or the golden rule level of capital per worker. Why it's called that, I don't know. But it's the one with maximum consumption. The way you find it mathematically is really simple. It is the one where the slope of the production function is equal to the slope of the depreciation function. Take the derivative of both, set them equal to 0. The slope of this function is the marginal product of capital, so you're looking for the condition where that is true. Let's see. Transition to the golden rule. You can look that over. It's not terribly complicated. Okay, next thing we add to the model is population growth. We're dividing through everything by L. Well, what happens if L gets bigger? If you have 100 units of capital and your population doubles, then capital per worker has fallen to half of what it used to be. So if now we're allowing for population growth. If the population can grow, then your steady state, where you're neither gaining nor losing capital per worker, has to equal the depreciation rate. You still have to replace capital that wears out, plus you have to add capital for all the new workers. Because if you don't, your capital per worker will drop. Not because you have less capital, but because you have more workers. So, if you allow for population growth, your steady state is now investment to replace both of those. Let's see. Here. Now, to be in a steady, to keep the level of capital constant, you need to replace not just the fraction of capital that depreciates every term, but also the amount you need to keep the capital per worker the same. What this does is it just shifts this line shifts its angle from that, for example, up to that. And this is now the steady state level of capital at that savings rate with this rate of population growth and that depreciation rate. If your population growth rate increases, N2 is bigger than N1, it just moves your steady state. It moves the amount of capital on a per worker basis you're losing each term from there to there, which means if your savings rate stays the same, your steady state level of capital per worker, and thus consumption per total output per worker, will fall from K1 to K2. Does this make sense intuitively? Let's say your economy is in a steady state, you have a certain standard of living, and all of a sudden your population explodes. Well, everything's going to be divided among more people in this very simple model. So this version of the Solow model, including population growth, predicts countries with a higher population growth rate will have lower levels of capital and income per worker when they're in steady states. Well, yeah, that looks like a pattern to me. And the golden rule level of capital stock, when you allow population growth in the model, it's the same thing, just with the addition, instead of the steady state being the marginal product of capital equaling the depreciation rate, it now has to equal depreciation plus population growth. This is sort of reminiscent of Malthusian beliefs. Boy, I wish we had the whole class time together so I could discuss this more. In very broad terms, the Malthusian perspective is population growth leads to disaster because the amount of stuff you have gets divided among more people, which allows them to procreate more, which dilutes the resources per person more, and it leads to collapse. This is wrong. There is a book. You're going to have to do a little research on your own time, read summaries of it. If you're ambitious, buy it and read it, called Guns, Germs, and Steel. Where is it? This was the paper it was based on. Population growth and technological change. 1 million BC to 1990. Now, if that isn't an ambitious title, I don't know what is. The book, Guns, Germs, and Steel. It explains economic growth from a different perspective. One of the main insights of the book, and the one that relates to the Solow growth model with population growth, is that the fundamental source of prosperity isn't capital. It's the human mind coming up with new ideas. More people means more minds, more Einsteins, more Elon Musks building rocket ships, more great ideas. And ideas are not a rival good. If you have 100 toasters or 100 bowls of food and you add more people, yeah, you have to, each person gets fewer toasters, less food. But if you add more people, and each person has one good idea, well, you don't have to divide the ideas among more people so that each person has fewer ideas. One good idea can be used by multiple people at the same time. If your society is producing one good idea a year and you have 100 people, 100 people can use it. If you have 1 billion people, 1 billion people can use it. And since the rate of knowledge production is a function of the number of people, it's not a diminishing resource. The more people you have, the more good ideas you have, and the more people you have to exploit them. So a larger population actually produces higher rates of growth. The book is more complicated than that, but that's the core perspective. Okay, that's it for this excessively long lecture on this chapter. See you next time.